Good morning, students. We have been discussing about the program control instructions, correct? The program control instructions that are used to control the order of execution of a program. When the program is executed, the instructions are executed in a sequential order, and these instructions are used to change the sequence. Okay, and we discussed about this branch instruction, jump and skip. And then, we also discussed about compare and test. The compare and test instructions are used to test some conditions, okay, by comparing or by performing AND operations. The operands are tested or compared, and these instructions are used to set the flag, okay, used to set the status conditions. And some status bits that are set as a result of some operation that ALU performs are overflow, okay, bit overflow, that is denoted as V here, and is it 0 condition. Is it is set to 1 when the bits are 0, and when the bits are all not 0, it is set to 0, okay. And sign for positive and negative, and carry, the bit C, the status bit C is used to C if there is a carry after the operation. So these are all the status bit maintained with the ALU that shows the status of the operation, arithmetic or logical operation performed. Okay, and here I also want to tell you about this program status word, okay, PSW. You need to know this. The bits V, Z, S, and C, okay, these are the bits that are used to, that show the status of the arithmetic operation that is performed, right? And in the same way, we have other status bits that are maintained in the central processing unit, like mode. Okay, there is a bit that maintains the status of the CPU. This shows the mode of the operation of the CPU. The CPU may operate in the user mode, or it may operate in a supervisor mode. CPU is normally in user mode to execute the user written instructions. But when the computer has to execute the operating system instructions, okay, the instructions that are at the higher level that belong to that are a part of operating system, that time the CPU has to switch to the supervisor mode. Okay, so this bit, okay, let's say this is the mode bit that is set to 1 or 0 depending upon the mode the CPU operates, okay, supervisor or user mode. So, and we also have other status bits that shows the status of the CPU. So what is this program status word? It is the combination of all these status bits. Okay, the combination of bits means program status word includes these bits, okay, bit V, overflow bit, 0 bit, sign, and carry, that shows the status of the result of an operation, and the mode bit that shows the mode which the CPU is operating in at that moment, okay, whether it is in user mode or in supervisor mode. And if even we also have other status conditions that that shows if the interrupts that are given as a request during execution of some normal instructions, okay, if interrupt is allowed or not, okay. So the status of the CPU, this PSW, program status word, is a group of bits that include all these status bits, okay. So all these status bits together form the program status word, and that shows the condition of the CPU or the status of the CPU. Okay. And we also know that this branch, jump instruction and skip instruction, correct? All these instructions can be conditional or unconditional. Okay, without giving condition, we can just branch to some other location during execution of a program, or it can be based on some condition. So if it is when conditions are given, okay, we are taking one instruction, branch instruction, okay, and when this instruction is given with condition, how this can be written, okay, for different condition, checking how this branch instruction can be written. Okay, that is what this is given in the table. The mnemonic BZ. Okay, this is the branch instruction that branches or this takes a control to another location depending upon the bit status bit Z. Okay, depending upon the value in the status bit Z. What is it? Z is 1 if all the bits of the operand are 0. Okay, all the bits of the operand are 0, it is 1. Status bit Z is set to 1. Otherwise, it is 0. So BZ is branch if 0. Okay, how this condition is checked? The status bit Z is checked. If it is 1, then it branches. BN is it. Always this letter B denotes branch, N denotes not. Okay, not or no. And all the other letters, you know, Z is for Z flag and C carry flag. Okay, P that, yeah, we will see. So branch if 0 and branch if not 0. Okay, this branching is done by checking the Z flag. If Z is 1, that means the bits are 0, so branching is done for this instruction. And branch if not 0, okay, if the instruction is B and Z, means the branching has to be done if the bits are all not zeros. Okay, so if we check the Z flag, if it is 0, means the bits are all not 0, then branching is done. And BC, okay, the mnemonic BC, okay, this is used for the instruction to branch if carry. Okay, if there is a carry out of the operation, then we need to branch to other location. Okay, so the carry bit is checked. Okay, status bit C is checked. If it is 1, means there is carry, so then branching is done. And the next instruction is B and C, branch if no carry. Okay, then the status bit C should be 0 here. Okay, so the tested condition is we check if C is 0. If C is 0, then branching is done. And BP is branch if plus. Okay, P and M are used for plus and minus here. So S here for checking sign, we check S flag. If S is 0 means it is positive plus. S is 1 means it is minus. Okay, so then if these conditions are satisfied, branching is done. And BV, the instruction, okay, the mnemonic used is BV here. It is for branch if overflow. If there is an overflow after performing the arithmetic or logical operation, if there is an overflow, then branching has to be done. Okay, that is done by checking the V flag. Okay, if B is 1 means there is overflow, then branching is done. And B and V is branch if no overflow. Okay, so these are the instructions that are, okay, branching instructions that are executed based on these status flags. And here there are two operands A and B, and we need to compare these operands, okay, the values of these operands, and based on that we need to branch. Let's say branching is to perform A minus B, okay, subtract. Before subtraction, we are checking if A is greater than B or B is greater than A or both are equal or A is less than B. Okay, these conditions are checked. So the instructions used are BHI. The mnemonic here is BHI. This is for unsigned. Okay, the mnemonics are different for signed numbers and unsigned numbers for comparing A and B. Okay, so here this particular column, part of this table shows the compare conditions, okay, for unsigned numbers. And the second part shows the signed compare conditions. Okay, for branching, we check if BHI means branch if higher. Okay, when the numbers are unsigned, it's just from 0, 1, 2, it grows higher, the numbers grow higher, right, or lower. Okay, so we check if higher, branch if higher. Okay, how it is done? By using compare condition, right? The values are compared here. And based on that, the result may be 1 or 0. Okay, when we compare this, it's a logical operation is performed, and based on the values of A and B, the result of this may be, if A is greater than B in this condition, if A is greater than B, the result would be 1. If A is less than B, it is 0. So if A is greater than B, if the result is 1 here, this branching is done. And the second one, branch if higher or equal. Okay, means higher or equal. A is greater than or equal to B. Okay, A is higher or equal than B. Then this branching is done. And BLO for branch if lower, means A is less than B. Okay, the value of A is lower than the value of B. And lower or equal is written as BLOE. Okay, and BE is the mnemonic used to branch by checking the condition if A is equal to B. And B and E is branch if not equal, if A is not equal to B. And for signed numbers, okay, when we use signed numbers, the conditions are compared by using this instruction. Okay, compared and branching is done by the instruction BGT. Okay, the mnemonic used is different here. It is greater than. Okay, because why we use greater, less, and here higher and lower here. If suppose we compare, if A is -2 and B is -3, here it is, the number is higher here. Okay, but still this is greater than -3, correct? -2 is greater than -3. So because these are signed numbers. So it is written as BGT for checking greater. A is greater than B. And BGE greater than or equal. BLT for less than, LE for less than or equal, and BE. These are same as the previous for unsigned numbers, how we used for unsigned numbers. BE for branch if equal, BNE for branch if not equal. Okay, so this way these branching instructions, okay, branching, jump instruction, and skip, all these instructions can be used with conditions. By checking condition, we want to branch based on the conditions that we check. Okay, it may be the result of the condition may be checking the status of the operation. After performing an operation, what is the result? Okay, based on that, we want to perform some operation. So the branching has to be decided based on these status bits. Okay, what is there in Z? What is there in sign? If the result is positive or negative, based on that, the branching has to be done. And or if suppose the operands, before performing the operation, the operands are compared and checked, okay, tested. So for that, we use this compare conditions. Okay, so based on that, we want to branch only, we want to perform subtraction only if A is greater than B. So we use the, what is the instruction we use here for branching? BHI. Okay, if it is an unsigned number, if the numbers are unsigned, and we want to perform A minus B only if A is greater than B. So this case, we use the instruction BHI. We write the instruction BHI address. So this, the control will move to this address. Okay, only if the operand A is greater than B. If not, if A is not greater than B, this branching will not be done. It will, the sequence, it will execute the next instruction. So we have taken one branch instruction and included all the conditions here. We have seen these instructions: branch, jump, and skip, and then compare and test for setting the status conditions. And now about this call and return. Okay, as I told you, call and return instructions are used with subroutines. Call is to call a subroutine. Subroutine is a subprogram, right? We are executing a program. We call it as a main program. And from that program, we want to execute another set of statements, okay, that are separately kept. So that is a subroutine. So to execute that, we use the statement call. And once those statements are executed, control has to return back to the main program where the call statement was given. Okay, so to return, we have this return statement. Okay, this return is used in subroutines to return back to the main program. Call is used in the place where we have to, where the control has to move to subprogram. We'll learn about this. Subroutine call and return. Okay, the subroutine call, this can be referred using these different names: call subroutine, jump to subroutine, or branch to subroutine, branch and save return address. Okay, all these means the same. Let's say this is our main program in memory. Okay, we have a series of instructions, and this is starting at location 1000. And we have the statement used as call, right, to call a subroutine. And we have a call statement that calls the subroutine S1. And let's say that, yeah, this is at 1005. Okay. And we let's say that there is a subroutine S1, okay, that is starting at this address. In memory, in the same memory, we have this part of subroutine that is starting at location 2000. Okay, so this is the first statement, first instruction of subroutine S1, and we have the statements. Okay, so here when the call statement is given to call a subroutine, means to branch to the this particular address. What is S1 here? S1 is 2000. Okay, so when this statement comes, when this call statement is executed, now PC program counter will have this particular address, right? 100 and 1005. And when this statement is, when this instruction is fetched, PC will be incremented and it will be pointing to the next instruction. So this is our next instruction that is to be executed. Let's say this is 1006. Okay, that is the content of PC now, program counter. And when this is fetched, yeah, PC is incremented, but during execution of the statements, it is found that it is call. Okay, the instruction given is call. And this is to branch to the subroutine to address 2000. Okay, so immediately the PC has to be loaded with this address, right? How the subroutine call can be implemented? To move to this particular address, PC has to hold this address, okay, to execute this instruction. Okay, so PC has to be loaded with this, but PC has the address of the next instruction. Okay, after the subroutine, we will have a return. The last statement is, it may be explicitly given in subroutines in some places, or it may be implicitly specified. Okay, always subroutine, after executing those instructions, it has to return back to this place, okay, to the main program. What is this address? Return address is 1006. What is there in PC now? So this need to be saved. Okay, so the first step is, before loading the branching address 2000 into PC, we need to save this address, okay, in some temporary location that is currently there in PC. Okay, that is a return address. So this has to be saved first, and then the branching address 2000 is moved to program counter. Okay, when program counter is loaded with this address, we know that the next instruction that is to be executed would be this. Okay, automatically the execution of subroutines. Okay, all the instructions in the subroutines one by one will be executed. And when there is a return statement, okay, when this statement is executed, it looks for the address, okay, return address, and the control moves to this statement. That is the statement next to this call, subroutine call statement. So the two operations that are performed are, the address of the next instruction that is available in the program counter is stored in a temporary location. Okay, the address that is there in the PC, that is the next instruction that we call a return address. Okay, that has to be stored in a temporary location. That is the first operation. And the second operation is transfer the control to the beginning of the subroutine. How we transfer the control to the beginning of the subroutine? By loading this address. Okay, the beginning address of the subroutine that is specified in the call instruction, moving that address, okay, into PC, program counter. So this way the control is transferred to the beginning of the subroutine. So these are the two main operations that are done when we call a subroutine, and to execute those instructions and return back to the main program. And when we see the locations, we have seen in the first step that the address that is in the program counter, that is a return address that need to be stored in a temporary location. So what would be the temporary location to store that address? Okay, it can be stored in the first memory location of the subroutine. Okay, when a subroutine is called, okay, here our call statement is call S1. S1 is our subroutine, okay, that starts at location 2000. So this is the first, what is the first location of subroutine? It is 2000. So when it is called, the control branches to that place and stores the content of PC, okay, that is 1006 here. And from the next statement, it increments PC by 1. Okay, loads this into PC, 2000 into PC, and increment PC by 1 and start executing the statements. Okay, this way, the first location of the subroutine can be used to store the return address. Okay, so when this return statement in the subroutine is executed, the address that is stored at the first memory location in the subroutine, okay, that is used as the return address. Okay, so the control return to that particular place. So first memory location of the subroutine, or the address can be, return address can be stored in a fixed location in memory. Okay, any particular location. Let's say the first memory location, 0th location in the memory is always to store the return address, or it may also be stored in a processor register. Okay, a processor register can be used to store the return address, and the other way is to store it in a memory stack. So in memory stack, it can be stored. Yeah, return address can be stored in one of these places. Okay, but the most efficient way is this, storing it in a memory stack. Okay, why is it more efficient? When there are nested subroutines. Okay, here we are calling, yes, here there is a subroutine call in the main, this is our main program. Okay, here is a subroutine call to call S1. And let's say here S1 is executing, and here again there is a call statement that calls subroutine S2. Okay, so we have in memory, we have in some location, we have subroutine S2, and it is starting at location, yeah, 3000, let's say. Okay, and here there is a return statement at the end that returns to the place where from where it has been called, right? It has to return back to, because here this call statement in S1 allows the control to branch to this particular address and execute these set of statements. And where this return, what is the next instruction here? This is the next instruction to be executed. Okay, let's say it is 2003. So the control has to return back to this particular address, not to the main program, right? So when we store it in a stack, to make you understand this, let's say we have a stack in memory. Here, when the main program calls S1, okay, what is the return address? It is 1006. It is stored in the first location in the stack. This is stack pointer will be pointing to this. And the control moves to location 2000 to execute S1. And when the subroutine S1 is executed, there is a call statement that calls the subroutine S2. Okay, the control has to branch to S2 to the location 3000. And it also has to store the return address. Okay, we are talking about storing the return address in stack. So here return address is 2003. Okay, this is the place where the control has to return back. So here the push operation is done, right? Push is to insert any data into the stack. So to insert this address now, 2000, the return address to subroutine S1, okay, that is pushed into the stack. And the pointer SP, stack pointer, will be pointing to the top address now. So now there is the control moves to 3000 after saving the return address in stack. It executes this instructions in S2. And there is a return statement in S2. Okay, so here where the control has to return first, it has to return to 2003 to this location, okay, in subroutine S1. That is stored at the top of the stack here. Okay, that is easily found at the top of the stack. So this address, the pop operation is done, and this is removed. This is moved to PC. Okay, 2000, because the program counter has to be loaded with the address. That way the control can be taken to that address, right? Okay, pop operation is performed to remove this. So PC will be loaded with this address, and SP is decremented. Okay, stack pointer will be pointing to this address. This way control returns to this. And when this S1 is finished, execution of the instructions in S1 is over, there is a return statement. Control has to return to main program. Now we have in the stack, top of the stack, we have the return address to return to the main program. So now this is the top value, okay, that is in the stack is removed and stored in program counter. Okay, so once PC is loaded with the address, control can be taken back to the actual program. Okay, so these are all the locations used, and here how the stack storing the address in stack and branching to the given to subroutine is implemented. The micro operations for call, okay, when call statement is call instructions executed, SP, the stack pointer is, okay, when it is memory stack, okay, if the address is, if it is starting from 50 and let's say this is 200, okay, and SP need to be decremented to insert, okay, when we have to insert another value into the stack, SP need to be decremented because it is 200 and it has to go to 199, the previous location where we can insert. Okay, the addressing is given the address as the stack grows, the address is decreasing. Okay, address is in the decreasing order. So SP is SP minus 1. And to move the return address that is there in PC into the stack, we write the instruction memory word at stack pointer at the location of SP. SP is this, right? Okay, right. So here the return address need to be moved. PC is moved, and then PC is loaded with the effective address. What is effective address? The address given in the instruction in the call statement. Okay, it is call S1. S1 is 2000. Okay, the address is 2000. So that is our effective address. So that is loaded into PC. Okay, this way call instruction can be, means calling a subroutine can be implemented. These are the micro operations performed. SP is the stack pointer is decremented to move to the next location, top location. And in that location, okay, the location of SP in memory, PC has the return address. Okay, next instruction. So that is loaded, that is moved to the stack, and PC is loaded with the effective address. Okay, that is effective address here is the branching address. Okay, so when the branching address is, when PC is loaded with the branching address, the next instruction that is executed would be that particular instruction. Okay, pointed by PC. So this way call statement is implemented, and return. Okay, when this return statement is executed, that is given at the end of the subroutine to return back to the main program, the top address that is there in the stack, okay, is removed, right? Here we perform pop operation, and in this case to call push operation is performed. Okay, so to perform pop, what is the micro operation? What all the micro operations need to be done, performed here? The memory word at location SP, that is the top location in the stack, that need to be moved to PC, that is the return address. and SP is incremented. Okay, after removing this particular value, okay, SP need to be decremented. So SP will be pointing to the previous value. Okay, when it is incremented, it moves down. Okay, so SP is incremented. This way, return from the subroutine to the main program is done. Any doubts in this? We have discussed about the branching. Okay, the program control instructions. Branch, jump, both are same. Okay, used in a same way. And skip. Skip is to skip the next instruction. Okay, one instruction. And it also can be, it is a zero address instruction. Skip is a zero address instruction. But conditions can be checked. Okay, skip if zero, skip if positive. Okay, this way, same way how we discussed here for branch, same way skip instruction can be associated with conditions. So based on that, based on the conditions, the skipping of one instruction, the next instruction is done. And we have seen the compare and test conditions. Okay, that compares by subtraction. Okay, by subtracting the operands, or by test. Okay, test operation. Test the operands by performing AND. Okay, and set some status conditions. And we have seen how the status conditions are set. Okay, after performing the operations by ALU. And subroutine call and return instructions. Okay, that are to call or branch to a subroutine and return back to the main program, to the called location. Any doubts in this? So we'll move to the next topic. Our next topic is program interrupt. This program interrupt refers to the transfer of program control from a currently running program to another service program, okay, as a result of an internal or external generated request. Until now, what we have seen is branching to some other location, right? From when a program is being executed, the branch instructions, okay, branch type of instructions will take the control to some other location. That is by the execution of the statements like BR or escape, IP skip instruction. But here it is not associated with the program that is being executed. Some request is, okay, a signal is sent to the CPU. It may be an external signal or internal signal that initiates the execution of the service program. Okay, that is to avoid, these are mainly used to avoid the errors, okay, unwanted errors that occur during the execution of program. It stops the execution of the current program, and the control is taken to a service program. Okay, we call this interrupt service routine. Okay, that this instructions given in the interrupt service routine is executed, control returns back to the actual program. Okay, so control returns to the original program after the service program is executed. An interrupt procedures usually stores all the information necessary to define the state of the CPU rather than storing only the PC. Okay, in the earlier cases, when branching is done, we have seen that when a subroutine is called, this program counter to return, the program counter will have the return address. Okay, so the content of PC is saved. Okay, it is stored in some temporary location and the branching is done. But here the state of the CPU is saved. Okay, before branching, before the control has been taken to execute the service routine, the state of the CPU is stored. The state of the CPU is determined from the content of the program counter and the content of the processor registers. Okay, what all need to be stored before the control moves to execute the service routine. The content of PC, content of the processor registers, and content of the status bits. Okay, that is the program status word. The program status word. Okay, the combination of all status bits that defines the state of the CPU, right? PSW is the status word that defines the state of the current state of the CPU. So that need to be stored. And the content of all the processor register and the content of the program counter. This is content of program counter is stored to return to that address again, to the main program again, okay, to the currently running program. In addition to that, okay, this we do for every branching, means subroutine calls. But here, when the interrupt signal is given, the currently running program is interrupted. Okay, it is paused for some time, and the control moves to the interrupt service routine to execute those instructions and returns back to the interrupted place. So before moving to the branching to the to service the interrupt, okay, to execute the interrupt service routine, the state of the CPU has to be stored. Okay, the state of the CPU includes the content of PCU, content of all the registers, and content of the status bits. And the interrupts, types of interrupts may be an internal interrupts or external interrupt or a software interrupt. What is this external interrupt? First one, external interrupts are initiated from the outside of CPU and memory, not from the internal system. It comes from the external units, such as IO device or a timing device. Okay, so example, the interrupt that is initiated by the IO device. It may be data transfer request or data transfer complete request. When there is a data available in the input register, okay, the input device, the user has entered some data through the input device. The CPU is executing some program, and there is a input data, okay, available in the input register. So that time input device initiates a interrupt, okay, to stop the current program, execution of the current program, and to accept the data. Okay, the computer has to accept the data, okay, so that the input can be taken for processing. Okay, so this is an external interrupt that is initiated by the IO device. Data transfer complete. Once the transfer is completed, okay, or it is transferred to output device. Okay, once it is done, output, it initiates an interrupt signal. Okay, so this is an external interrupt. And timing device, when we perform some operations in a computer, operation timed out. What is that? What is that error? What is that message we get? Operation timed out. Okay, that is because of, that is a result of execution of some interrupt service routine. Okay, interrupt services routine is written in a way to display that message. Okay, operation timed out. When an instruction is executed, okay, for a long time, but it's not complete. Okay, there is some problem to complete that instruction. So how long the system will wait? It has to go to the other instruction. So that time the program is interrupted. The execution is interrupted. The interrupt service routine is executed. That gives the message operation timed out, and it stops at execution. Okay, and moves to some other program, execution of some other program. This way, the error. Okay, otherwise, what does the error occur in this case? Timeout cases. The CPU will be keeping on holding that instruction, okay, which is not getting completed. Okay, the other processes would be waiting. So it has to be stopped, interrupted, okay, after a particular time. So that case, this interrupt is initiated. Timing device initiates the timeout interrupt. And power failure. In case of power failure, okay, the maybe the programs that are running need to be saved and interrupt is initiated to stop the error that occurs. These are external interrupt, and internal interrupts are caused by the currently running program. Okay, when the CPU is executing some user written programs, and through the program, the user is trying to store some data into the register or some stack, and there is stack overflow. Stack is full. What is stack overflow? Means the stack is full. Okay, before storing into the stack, we check for stack full condition. Okay, if the stack is overflow or underflow, if the stack is empty, and the user is trying to remove data from the stack, then the error message has to be given. Okay, so that kind of interrupt that occurs during the execution of some program. Okay, we call internal interrupt. That is not initiated by the external units. It is initiated by the currently running program. And divide by 0. There is an operation in the program. Okay, the operation to be performed is dividing. And when this division, we are trying to attempt this division by 0, okay, which cannot be done. So that case, the interrupt is initiated, and invalid operation code and protection violation. During the execution of program, we are trying to access some data which is protected from the user. The user is not allowed to access, okay, but trying to access the data. So that causes the violation of protection. Okay, so this kind of interrupts are called internal interrupts that are initiated by the currently running program. And software interrupt, it is initiated by the software. Okay, here both internal and external interrupts are initiated by the computer hardware. Okay, and the software interrupts are initiated by executing an instruction by the software. Okay, one example is supervisor call. In a case during the execution of some user written program, when the CPU is in user mode, if it has to switch to supervisor mode, okay, to execute some operating system instructions, this is initiated, this interrupt, okay, supervisor call. That is a software initiated interrupt, okay, by executing instruction the system. Okay, so this is software interrupt. Okay, these are the types of interrupts. External interrupts initiated by external units, internal interrupt initiated by the system. Okay, internal operation by some internal operations that is happening in the system, the interrupt is initiated. Okay, these are all initiated by hardware. Even though the interrupt is caused by the running program, okay, the hardware initiates the interrupt. Okay, that's about interrupts. If you have any doubts, you can ask me now. I'll check the attendance meanwhile. Yes, any doubts in this, what we have discussed today in program control instructions and interrupts? No doubts. Okay. Yes.